Hi everyone. So here is lesson 3.5. This is the last section in chapter 3. Just a reminder that you will have your chapter 3 test in the next class, okay, on Monday. So let's begin. Complete the first two columns of each table of values and sketch the graphs below. Do you notice any differences in their appearances? Okay, so we have, so the first table of values, things got shifted here, is for the relation y equals to 3x, and the second table of values is for the relation y equals to x cubed, all right? So let's work this out. 3 times negative 2, negative 6. 3 times negative 1, negative 3, 0, 3, and 6. So here are your y values. Recall from your previous lessons, we have talked about how we can calculate the first difference. Here we're showing this as delta y, okay? So we start from the second row. We take negative 3, subtract the previous row, negative 6. This is really negative 3 plus 6, so that's 3, correct? Okay, one more. 0 minus negative 3. This is 3 again. The next first difference, 3 minus 0 is 3. 6 minus 3 is 3. Let's graph this relation. So here, let's use red for points. Negative 2 and negative 6 is here. Negative 1, negative 3, 0, 0, 1 and 3, 2 and 6. All right, so let me put the line here. May not be perfect for now, but we can fix it anyway. Okay, so let's put arrows on the line as well. So obviously this is y equals to 3x. Let's label the x-axis and the y-axis. So we have completed the first graph, and obviously this is a linear relation. Okay, so now let's move on to the second relation. Here we have y equals to x cubed. So remember, this means x times x times x. Negative 2 times negative 2 times negative 2 gives us negative 8. Negative 1 cubed gives us negative 1. 0 cubed, 0. 1 cubed is 1. 2 cubed is 8. All right. So once again, let's work out delta y, the first difference. So negative 1 minus negative 8. This is really 8 minus 1, 7. 0 minus negative 1, that's 1. 1 minus 0 is 1. 8 minus 1 is 7. Okay, now what if I continue? Well, if x is 3, I get 27. 27 minus 8, that will be 19 already. Okay, so we can see that the delta y values, the first differences, are not constant in this case. Well, what does this look like if I try to plot the points? So let's see, negative 2, negative 8 is here. Oops. And then negative 1, 0, 0, 1, 1, 2, 8. And then 3 will be like all the way outside of the graph. And let me try to connect these points. I cannot join them using a straight line, so we don't want broken lines. We want to join these using a smooth curve. So notice I said smooth curve. Okay, so here's your x-axis, here's your y-axis, and then let's label the graph as y equals to x cubed. Okay. So here in the brown section, it tells you delta y is the first difference, like what we have done before. You always take the previous row and subtract the current row and subtract the previous row. Okay, now what do we notice though? We notice that in the first relation, y equals to 3x. This one, it has constant first differences. And when this is the case, we notice that the graph is a straight line, and this is a linear relation. On a graph of y equals x cubed, we saw a curve instead of a line. And we also noticed that delta y, the first differences, are not constant. So constant meaning not the same. So you hear this word a lot in math, right? Something's not constant, that means they're not the same. Okay, so what does that mean? That means that we will see a curve instead of a line on a graph, and we call anything that doesn't look like a line on a graph a nonlinear relation. Okay. What's something else that we can, talk about? Well, I think it also has to do with, the equation that we have. In the equation of y equals to 3x, y equals to 3x, it gives us a linear relation, and we notice that the exponent of x is 1. So that means we actually have a degree 1 polynomial. Well, monomial in this case, but this basically applies to any degree 1 polynomial. But when I look at y equals to x cubed, which gave me a nonlinear relation, we can say that this is not any nonlinear relation is not a degree 1 polynomial. So you might be wondering, like, what do you mean? Well, for example, if I have y equals to 4x squared plus 2x minus 1. Well, don't you have an x in there? Yeah, but I also have an x squared in there, right? So this is a degree 2 polynomial. When you graph this out, it will be a curve. If you have 4, why do I like 4? No, let's change it. What if I have like something like x minus 1, x plus 1, when I multiply them together? Now I see degree 1, right? X. But when you expand this, it's x squared minus 1. So this is still another example of a degree 2 polynomial. So this is still a nonlinear relation. Okay, so when we talk about the degree of the polynomial, we're referring to the expanded form of the relation. Okay, so be careful with that. So now we know that we can rely on the first differences or the degree of a polynomial to indicate whether we have a linear or nonlinear relation. Let's take a look at the 4 relations here in example 1. Okay, so y equals to 3x plus 2, linear or nonlinear? Of course, it's linear. Good, because it's 3x plus 2. Now what about the next one? X to the 4 plus 10x equals to y. Because we have a power 4, this is also nonlinear. How about 3x minus 2y equals to 11? It's not that hard to tell, right? So even though it doesn't look like y equals mx plus b, all I have to do is look at, okay, so y has degree 1. So basically, if I rearrange this, and then I have to divide everything by -2, I will still get this form, or you can rearrange it to say you have 3 over 2x minus 11 over 2. Either way, this is still a linear relation, right? Because the degree of y is 1. This is also 1 here, okay? Now in question D, 4y squared plus x equals to 1. So power of x is 1. It must be linear. Be careful, because now if I want to isolate y, what will have to happen? I have to divide by 4, and what else? I have to square root both sides of this equation. So that means x won't be just x to the power of 1. It'll be some kind of square root of x. So for that reason, this is actually a tricky one. This is also nonlinear. Okay. Example 2. So let's identify whether these relations shown on the table of values are linear or nonlinear. We don't want to make graphs if we don't have to. So let's calculate the delta y, okay, the first difference. Once again, -8 minus -4. -8 plus 4, -4. -12 minus -8, so -12 plus 8 is -4. -16 minus negative, so plus 12, -4, -4. So because delta y is constant, this is linear because you have constant delta y. Okay. B. So the x column, 1, 2, 3, 4, 5, everything goes up by 1, so that's good. So 4 minus 1, 3, 9 minus 4, 5, 16 minus 9, I don't know, 7, 25 minus 16, 9. So obviously, this is non-linear. Question C. The x column is going up by 2, 4, 6, 8, 10. So they're still going up by a regular interval, so that's fine. Okay. And then delta y is 17 minus 11, 6, 23 minus 17, 6, 6, 6. Okay, so constant again, these are linear. And then finally, in D, the x column is going from 5, 4, 3, 2, 1. But again, because they're going down by 1 every time, so we just have to see whether first differences are constant in order to figure out whether this is linear or not. So plus 2, plus 2, plus 2, plus 2. This is still linear. Okay, so we have 3 linear, 1 nonlinear relation. Trick question, like bonus question now. What if I want to find a rate of change or the slope of each one of these relations? Well, I can't find the slope of a nonlinear relation, but what about the linear ones? Okay, so that one, I recall that slope is delta y over delta x, or y2 minus y1 over x2 minus x1. Well, in the first relation, delta y is -4. And then what's delta x? 2 minus 1 is 1. So this is -4. In C, what's delta y over delta x? Well, delta x would be 4 minus 2. So 2. 6 minus 4, 2, etc. Right? So delta y is 6. Delta x is 2. Slope is 3. And then for question D, now delta x is 4 minus 5, 3 minus 4. So these are all -1s. So that means slope here is 2 over -1 or -2. Okay. Last but not least, let's take a look at example 3. You may think, this question looks familiar. Yes, indeed. I think you've done it for homework. Okay, so altitude is represented in the first column, so we can use that as our independent variable. And then your dependent variable will be air pressure. Okay. We have these numbers. We can go up by, let's see, we need 8 in total. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I think we have to go by 10,000. Okay, and then for altitude, we have to go all the way to 30. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boxes, so I think I'm going to go up by 3. Okay, all right, so is the data linear or nonlinear? Well, let's plot. 1 and 80, so somewhere here. 3 and 60,000. And 6 and 40,000. 16, so somewhere here, 20,000. And then 22 is 10,000. And then 30 is 5,000, so halfway here. So clearly this is a nonlinear relation. Let's join the points using a smooth curve. Okay. So how does the graph shows the rate of change? Well, this is more like a description because we said that the rate of change of this relation is for a nonlinear relation is not constant. So we basically have to say that if you compare, let's say, the first 2 data points, okay, think about the rise over run. So look at that triangle. Compared to, let's say I pick 2 later points like here, second last and third last points, the rise over run in this section, okay, on average. It totally shows that the graph is decreasing more rapidly in the beginning, and then it kind of slowly decreases more slowly, right, in the later sections. So the graph does show that the rate of change is slowing down. As you can see, the trend is going from a more rapid decrease to a less rapid decrease, or go to like steep to shallow. If I have to describe a certain section, okay, the slope in the certain section of the curve. And then next, use interpolation to estimate the air pressure and an altitude of 20 kilometers. Interpolation is the key word that we use to basically say that we want to determine the value of a data point on this graph within the given data set, the range of the given data set. And so because 20 kilometers is between 1 to 30 kilometers in altitude, right? So it's kind of like somewhere here between 16 and 22. So we say that we use interpolation to make this estimation. So let me show that on the graph. At 20 kilometers, I can draw a dotted line to project up until it touches the curve that I have. And then what is the corresponding air pressure at this point? So this is roughly 20, make an estimation. This is lower than halfway between 10,000 and 20,000. So maybe 125, like that. So using interpolation, we found that the air pressure at an altitude of 20 kilometers is 12,500 Pascal. APA stands for Pascal. That's the unit for air pressure. Okay. Now, if I'm making an estimation from an altitude of, let's say, 35, it's outside of the range of numbers that we're given, then instead of interpolation, it's called extrapolation. Okay, like extra. So this basically is your section 3.5 lesson. For the rest of the period, you're going to work on your homework from this section and also the chapter 3 review questions. Okay, they are posted in the Google Classroom.